Hi, in this section of the course we're going to look at the notion of logical equivalence. One way of defining logical equivalence is in terms of the notion of logical consequence. And as you've already seen, logical consequence can be defined in two ways. One is in terms of proofs. If I've got an argument which leads from a premise to a conclusion, and it goes step by step, using valid means, in some proof system, we say that the argument is valid and we've got a proof which goes from the premise P to the conclusion C. And we write that with a little turnstile, a T on its side, to say that the conclusion C follows from P. On the other hand, we could define this notion in terms of models. And again, we say the argument from P to C is valid, but now, instead of defining it in terms of proofs, we say that the argument from P to C is valid if it's got no counterexample, if there's no way of making the premise P true and the conclusion C false. Let me give you an example of how we look at this if we have an argument which has actually got three premises, P1, P2, P3, and ends in a conclusion C. This argument is a valid one if we can do a truth table which might have a whole bunch of different rows depending on the values of the little propositions P1, P2, P3, whatever are in there. The details don't really matter. We'll see some other more particular examples later. We say that the argument is valid if you never have a row of a truth table where P1, P2, and P3 all get the value true and C gets the value false. If you've got a row like that, we say that the argument is invalid, and we'll write that with a slash through the turnstile. If there's no row like that, we say that the argument is valid, and it has no counterexample. So, if we've got consequence going in two directions, if I know that B follows from A, or B is a logical consequence of A, and A follows from B, or from B you can get A, then I know that I never have a case where A is true and B is false, that's ruled out, and I never have a case where B is true and A is false, that's ruled out. So look at what happens in this case. If you know that A is true, then because the case that B is false is ruled out, B is going to be true too. On the other hand, if I know that A is false, then in that case, the possibility that B is true is ruled out. So B's got to be false. And so, what you know is that the truth value of A and B stand together. They always have the same truth value. And this is what we'll call the notion of logical equivalence. So here's the definition. Two formulas A and B are said to be equivalent if and only if from A B follows and from B A follows. And we'll write this with a kind of double-headed turnstile. And this means that A and B are satisfied in exactly the same models. Satisfied is another word for made true. So all of the circumstances where A is true are circumstances where B is true, and vice versa. Let's work through an example. What I've got here are two formulas. This one, on the left, is a negation of a disjunction. It says it's not the case that either P or Q, and this one on the right is a conjunction of negations. It says not P and not Q. And what we'll do is we'll work through a truth table for both of these formulas. And so I'll do this in some detail. I'll have two columns on the left-hand side of the truth table where we'll look at all of the possible combinations of values of P and Q. So I'll have four rows, two where P is false and two where P is true, and the values of Q will alternate. False, true, false, true. So now I've got every possible combination of the truth values of P and Q. Let's first look at the negated disjunction. In this case, we'll have the truth values for P or Q, and we'll look at, are there any rows where either P or Q is true? On the first row, P or Q aren't true, so the disjunction gets a value false, whereas in the other three rows, one at least is true, so they get the value true. And then the negation gets the flip of those values, and I get a 1, a 0, a 0, and a 0. So this formula is true in the first row of the truth table and false everywhere else. Now let's look at the second formula. Now this is the conjunction of not Q and not P, and so for the values of not P, we'll take the values of P and flip them, 1, 1, 0, 0, and for not Q, we'll take the values of Q and flip them, 1, 0, 1, 0. Now for the conjunction, we'll compare these two columns and ask, is there any row where both of them are true? And the answer is yes for the first row and no for the other three. So what I end up with is 3 rows where the formula is false and 1 where it's true. And in fact, if I look at the value of not P and Q here in this column that I'm highlighting, and I compare that with the value of not P and not Q in this column that I'm highlighting, both of them agree. This means that the two formulas are equivalent. What that means is that they agree in truth value in absolutely every row. Here's the rows where they're true, and here's the rows where they're false. Let's look at another example, this time of two conditionals, P implies Q and Q implies P. If I do a truth table for this, it'll be a little bit quicker this time. P, Q, 0, 0, 1, 1, 0, 1, 0, 1. Conditional is true all the time except for when the antecedent, left-hand part, is true and the right-hand part, the consequent, is false. So P implies Q is going to be true, all except where P is true and Q is false, and then gets the value false. Q implies P is going to be true, all except where Q gets the value true and P gets the value false, which is the second row. And here we get an example of two formulas that are not equivalent. So I'll get my highlighter, and we will see that this row is one where P implies Q is true and Q implies P is false, and that will be enough to show that they're not equivalent. But this row is one where Q implies P is true and P implies Q isn't. So that also shows that they're not equivalent. So what we get is that P implies Q, that these are not equivalent formulas. In fact, P implies Q does not entail Q implies P. Q implies P doesn't follow from P implies Q, because here is a row where the first is true and the second is false, and doesn't go in reverse either, because here is a case where Q implies P is true and P implies Q is not. They were just two examples of logical equivalences. On this slide, what I've got here is lots of different examples of logical equivalences. And what would be a good thing for you to do is to go through these and convince yourself that they're all equivalent. So here, this one says that A implies B is equivalent to a disjunction of not A and B. This one says not A, the negation of a negation, has always got the same truth value as A. This one says that the order in which a conjunction happens doesn't matter. It could be A and B, or B and A, always the same truth value. This says that the order in which a conjunction is bracketed, A and B and C, Doesn't matter from bracketing the A and B first and then doing the C. Same for OR. In fact, I could have had A or B is equivalent to B or A, but I just forgot to put that one in too. This one says that stuttering, saying A and A, says nothing more than saying A, and nothing less. They have exactly the same truth value. Same for A or A and A. And these ones are, we've done one, but the other one works as well. This says a negated conjunction is equivalent to a disjunction of negations, or a negated disjunction is equivalent to a conjunction of negations. And this last one is interesting. It's what's called the distributive law. This says that A and B or C says the same thing as having the two options A and B, or A and C. You could either name the A first and have the two options for B or C, or you could name the A with the options. If you do these, convince yourselves that these things are equivalences, then you know a lot of propositional logic. So let's stop there.